Without further ado, I am pleased to introduce Elaine Stewart, a new volunteer with the Friends, and an aerospace engineer working at NASA Goddard on the James Webb Space Telescope. She has a bachelor's degree in chemical engineering from the University of Delaware and a master's degree in space systems engineering from Johns Hopkins. And she just graciously finished judging all of the science fair projects for the middle school in Arlington. Thank you so much, Elaine, for being with us today. We are all looking forward to hearing more about JWST.
Of course. Thank you so much for having me. I'm actually here at my office at Goddard Space Flight Center. It is in Greenbelt, Maryland, but I live just up the street from the planetarium. So I frequently bike by there and walk by there, and am really excited to go and visit inside of the planetarium sometime soon. Again, I am an aerospace engineer at Goddard, and I actually worked on the Webb telescope since 2016. So I started working on the telescope while I was still pursuing my degree at the University of Delaware, and I would come during the summers or during my breaks to be able to actually work on the hardware. And since graduating, I supported Webb full time, and I was actually at the launch site in French Guiana this past fall. So I'm going to tell you a little bit about the mission, a little bit about my role, and I'm really happy to answer any questions as we go throughout the presentation and at the very end. So thank you so much. Okay, so hopefully by now you've heard about the Webb telescope, but I'm going to tell you a bit about our science objectives and really the true feat of engineering that this telescope is. Here you can actually see photos from a couple of different locations that the telescope has been in. This photograph on the left is actually from Goddard Space Flight Center. So we have here the largest 10,000 class clean room in the world, and Webb is very contamination sensitive. So my role as a chemical engineer with an aerospace background is actually focusing on the material science and ensuring that these beautiful gold mirrors that we see are as clean as possible for the images that we will actually be getting back very shortly, since we are currently on orbit and almost finished with our alignments. On the top picture on the right, this picture is actually at Northrop Grumman, and you can see the sun shield is fully deployed underneath of that. So we have a 5-layer sun shield that is the size of a tennis court that actually helps to protect the telescope from the sun. So the science that we are conducting with Webb telescope needs to have the instruments operating at very cold temperatures. So the sun shield actually protects and provides that the thermal balance that we need to actually make those observations. Here it is showing the comparison of Hubble's primary mirror as compared to Webb's primary mirror. So the Hubble mirror is around 2 meters in diameter, whereas the Webb primary mirror is around 6.5 meters in diameter. You can also see that there are segments. So there are 18 different segments that are able to move and actuate. And that's actually what they're currently finishing right now. All the news coming out about Webb at the moment is about the final stages of alignments and preparation in getting those first images back from the telescope. Now, this is a little bit about the instrumentation that we have on board. So there are actually 4 different instruments, and we are looking in that near infrared and mid infrared wavelengths. So we have the near spec, or the near infrared spectrograph, near-ISS, near infrared imager, and the slitless spectrograph, near cam, which is the near infrared camera, and then MIRI, which is the mid infrared instrument. So currently Webb is at this L2 orbit. This is a great depiction to show you exactly where that is. For reference, it's about 1 million miles away, and you know, it was quite the journey for Webb to actually get there. It did some of its deployments along the way, and we launched on an Ariane 5 rocket because it was able to, you know, get us to this L2 orbit and actually be able to hold Webb in the fairing of its rocket. So Webb has a very unique design because it had to become an origami telescope to actually fit inside of that rocket fairing. Okay, great. So this is showing a little bit more about the observing side where the science is going to be happening. We want to look in those infrared wavelengths. So here you can see the primary mirror, the secondary mirror, and where these science instruments are actually located with this big tennis court sized sun shield. And then the sun facing side where we see the star trackers, our steering and control, the antennas that we are using to actually communicate with the Space Telescope Institute in Baltimore to send commands, translate the data, and get those observations that we're actually making from Webb. And then our solar power array. This is a little bit about the unfolding sequence. So you can see that there are actually some of the unfolding happened on its way to L2. But it was really exciting to follow along right after the launch while I was in French Guiana, and I got to see the rocket take off, and then we were watching the streaming of the control room and the cameras that we had on board. We actually did see the solar array deploy too, with that first separation, well, the final separation from the launch vehicle, which was really, really exciting. So we are now fully deployed and operational. This is all about how we talk to Webb. So I think that this is really interesting because, we're at this L2 Lagrange point, and I've had lots of people ask me, how do we actually communicate with Webb? So here you can see that we're using the DSN, or the Deep Space Network, and I have lots of coworkers. We have a whole entire crew that 24/7 is actually monitoring and talking to the telescope in Baltimore at that Space Telescope Institute. Webb has been a really incredible program to be a part of because it's an international collaboration. So I've had the privilege of traveling to other NASA centers, which has been within the US, but also with my experience in going to the launch campaign, I was able to work with our European Space Agency counterparts and the Canadian Space Agency counterparts that helped with the instrumentation. It's been really great to see that everyone wanted the telescope to be in its best performance function as possible. Working alongside all of our counterparts was amazing, and just really an incredible experience to have, to see that the commitment from everyone was present from all around the world in the excitement and the engineering work that went into this telescope. Okay, so now I'm going to get a little bit into the science that we're so excited to learn with Webb. Okay, here you can actually see a photo of the Eagle Nebula, and the demonstration on the left is in visible light, near infrared light, and mid infrared light. So you can see that this near infrared light can actually peer through some of the dust and the clouds and reveal more of the stars that lie behind it. So with the instrumentation that we have on Webb, we'll actually be able to see more than we were able to with the Hubble Space Telescope. We'll be looking into discovering some of the first galaxies that were formed right after the Big Bang. And we're also going to try and observe galaxies as they change over time. Look a bit more as to how stars are formed, how they exist, and also how stars die, with the ability to use those infrared light observations. And we're even going to look a bit more at our planets in our solar system. The infrared light observations also helps us to find distant planets too. And, some of the main things that we're super excited about is looking at our early universe, some of those first galaxies that were formed. How do those galaxies change over time? What is the star life cycle like, and other worlds? So with that, I will take any questions people may have. I'm happy to provide a bit more information and background, but yeah, thank you very much.
Okay, thank you, Elaine. If people have a question, you could unmute yourself and ask the question.
Yes, can you hear me?
Yes, I can hear you.
Yes, I was just wondering, they have now a newer telescope. How much more powerful is that one? That I think it's named after the Webb, who was a director at the Kennedy Space Center for a long time.
Let's see. I'm trying to think of what telescope you're thinking of.
Well, I think it was recently, I'm not sure if it was recently put into orbit or it's about ready to, but I know it's a much more powerful one, but I'm not positive of its power.
Well, I know some of the, like my mission that I'm supporting now at Goddard is actually called the Roman Space Telescope, and Nancy Roman, they call her the mother of Hubble. And the mirror size is actually exactly the same as Hubble, but it's a wide field telescope. So we'll actually be able to see a much greater field of observation with that telescope. And there's another telescope that is in the very early stages, but it is called LUVOIR, and it is actually a UV telescope. Now, my understanding is that they recently just combined it with some of the HAB-X efforts. And some of the most interesting, I think some of the most interesting studies you can look at are the decadal surveys that come out every 10 years. I think we just came out with our recent astrobiology decadal survey, and those decadal surveys will basically endorse what the next missions are that we really need to pursue in terms of the questions that we have. So Webb, this was the mission that was supported from its decadal survey. Roman has been supported from its decadal survey. So I'm sorry, I'm not quite sure if I know exactly which telescope you're talking about, but that's basically how each, flagship mission is chosen from those big questions that we have and that we want to answer.
So Elaine, could you tell us who James Webb is?
Yeah, so he actually was a NASA administrator. And what's interesting is that, I found with some of the missions, sometimes they'll be named after, the science that they're actually going to conduct. Now we have a mission here at Goddard that's called PACE, and this is actually looking at plankton and the aerosol environment and how plankton changes over time to really understand the carbon capture that happens in the ocean. Now, some of our larger flagship missions will be named for people that were really important to the field. Again, like Webb was a NASA administrator. He had a big part in influencing how NASA operates today. And then we have the Nancy Roman project that was named after Nancy Roman, who was really one of the main people that helped with the Hubble Space Telescope. So sometimes the acronyms will be indicative of the science or the mission that they're trying to accomplish. And other times it has to do with, someone that really had a big impact in this field or in this area of study that we're honoring with the telescope name.
Okay, and can you tell us what the greatest engineering challenge you faced when working on this telescope?
Absolutely. I think probably the greatest engineering challenge was that there were so many moving parts in terms of the actual hardware and the people involved in the hardware. We had contracting companies all over the US, we had international involvement, and each person involved had, a contribution and a piece of the telescope that they knew a lot about or were really passionate about. And we have systems engineers who ensure that the hardware every subsystem is going to work together. And in the end, all the hardware is going to operate as we expect. So I really think that one of the biggest engineering challenges coming in as, still a college student was understanding how the instrumentation of just, we're going to look in the infrared wavelengths, how that can actually be made possible by all of the surrounding subsystems. So we have the structure that goes around it. We have thermal engineering considerations, because there's quite a huge difference in the temperature between the sun-facing side and the cold operating side. So I think for me, it was really a big learning curve, but everyone was so helpful in terms of teaching me about the different subsystems. And with contamination, you really have to understand where your sensitive surfaces are and ensure that anything that is going to be nearby or could come into contact with it are just as clean as those sensitive surfaces need to be.
Okay, and then can you tell us the difference between infrared light and the, normal light?
Yeah, so let me go back a little bit. So we'll say that, this is not my area of specialty. We actually have a project scientist. His name is Dr. John Mather, and he has received a Nobel Prize for his work on a mission called COBE. And this is actually all about the cosmic background. So there was a mission that was sent out of Goddard investigating the cosmic background, and his predictions actually did match the measurements that they made. So his specialty is definitely, different wavelengths of light. But you can imagine that no visible light that we are able to see versus this near infrared and mid infrared, we need to alter just basically the wavelengths that we're looking at to see the light that is traveling from these distant galaxies and distant targets.
I have a question about the instruments that are on your sun-facing side.
Mm-hmm.
It's not too hot for them. I mean, clearly you want to keep, you've got the other side with the sun shield, but what about on the sun-facing side? Are those,
Yeah,
what are the tolerances of those devices for heat?
Yeah, absolutely. So we have a great team of thermal engineers, and what they'll do is they'll actually model to predict the temperatures that this hardware will experience, and then we test. So we go into a thermal vacuum chamber, and this testing for Webb, we actually split it up. So the telescope element, where you see the primary mirror and the secondary mirror, this whole unit was actually tested in Houston at Johnson Space Center. And then the sun shield was tested at Northrop Grumman in Los Angeles, California. So they will basically put it in that space environment and ensure that it is able to survive. Now they have a couple of different ways to mitigate. If they want an area to remain a bit cooler, sometimes we'll use like a coating. So they'll have a white coating that will reject the heat away. If you need an area to stay warmer, you can have heaters, or you could use, say, a black coating to actually help and absorb some of that heat in. So they have a couple of different ways that they're actually able to mitigate and monitor the temperatures. But at the Space Telescope Institute right now, they are constantly looking at what those temperatures are that the sun side is experiencing. It's very it's a big engineering challenge too, to make sure that all of your hardware is tested and will survive in the temperatures that it'll experience on orbit.
So what do you think you will gain, or the most exciting information you will gain from this telescope?
I think definitely some of the most exciting information will be looking back at those first galaxies that were formed. I think we've learned so much with Hubble, but this ability to even look past the dust clouds and learn a bit more about star formation, it's going to be incredibly exciting. Now, those are the direct science missions that we're trying to accomplish with Webb. But I think another program that not many people know about, they actually have an early release science program where anyone from the public, we have professors from around the world apply, we have different institutes apply for observation time. And if they are picked from this application process, then they will actually get observing time to look at their specific interest with Webb. So I'm really interested to see a bit more about what proposals were chosen, what will they learn with their observation time, and all of the information from the Webb telescope will actually be public. So we will be able to, rewrite some of our understanding of astronomy and how our universe really works.
So maybe they would be able to tell us if there's any unidentified flying objects or life on a different planet.
Yeah, so the life on a different planet is really interesting. We will have the ability to learn a bit more about some of the constituents that could be on another planet and might indicate that there is life of some form present. That has to do with, kind of the chemical composition that we see. And if we identify, this is an interesting chemical composition, and we'll look a bit more into it.
And what is the life expectancy of this telescope?
The mission lifetime right now is 5 years, but this could be extended. Now, one of the limiting factors is usually the propulsion. So having enough fuel if we need to make adjustments or when we are moving around to look at different targets. But they actually did an excellent job with the launch and saved a bit of the fuel that they were expecting to use from the start, which is really great. So should be 5, but they're hoping that it'll be closer to around 10 years for the mission.
And then once its life expectancy is gone, what happens to the actual telescope?
That's a great question. I think that's something that I'll have to look into a bit more. I'm not quite sure what will happen after the, life expectancy. And it's funny because, the Hubble Space Telescope had, I believe, a similar life expectancy, and it is still operational. So it could extend even well beyond 10 years. And there's even some, interesting studies in terms of possible future servicing of missions in space. And if there's developments in that area, then who knows, maybe it'll even further extend the lifetime of Webb.
So how does that lifetime expectancy compare with the number of years that it took to develop and build and test the telescope?
Webb has been in development for quite some time. I mean, I've only been working on it since 2016, so I can't quite talk about the background on it too much since I wasn't present for that. But I will say that something I really enjoy about working at NASA is everything that they learn with working on their missions, they actually apply to see, how can we help life on Earth too? I know from Webb with some of their work with the optics, they made some advances in, glasses and helping people with their eyesight. There's a whole part of NASA that focuses on, okay, we developed this technology for space. Can we apply it for something here on Earth, which is really amazing too.
Does anybody else have a question?
Why did you choose gold for the mirror? And the second follow-up question is, how do you keep all the moving parts lubricated in space?
Okay, so the mirrors are actually made of beryllium, which is a lightweight material. As you can imagine, it's quite a large structure, so it had to be lightweight in order to be able to be launched into space at an effective cost and fit in the rocket and everything. But the gold coating is actually so that it's reflective. This is so that we can actually make our observations. So if there's a galaxy or a target of observation, this light will actually be reflected from the primary to the secondary mirror and then into this, it almost looks like a little column. Back behind there are these pickoff mirrors where it then leads to the instruments. So the gold was necessary for it to be reflective, for us to actually make the observations. And then the second question was, how do you keep all of the parts lubricated in space? So there are aerospace approved lubricants, and especially the mirrors in terms of the actuations that they need to make to align the mirrors. We do all that testing while we're in those thermal vacuum chambers. So we ensure that, data has been gathered and we've confirmed that the lubricants that we're using, and there's sometimes heritage lubricants that have been used on different missions and we've seen success with them that have been applied to, so that we know, okay, even in the environment of space, it will be able to still operate as we expect it.
I've got a question here
Okay.
about the international collaboration.
Anyway,
What percentage is United States or NASA, and how much do the Canadians and Europeans input? And is there any difference of opinion and on that? And how much control now?
Okay, so I don't know exact percentages, but I will say that the Europeans helped out with some of the specific instruments, like the MIRI instrument, and then the Canadian Space Agency also assisted with an instrument. But the European Space Agency contributed the Ariane 5 rocket that we launched on, and we had our whole launch campaign there. So in terms of collaboration, I'm not quite sure about specific percentages, but there was, heavy involvement throughout every step of the way for it to be international collaboration, especially because when you're designing a telescope to go into a specific rocket, you have to make sure that you're meeting all of the requirements of the rocket that you're going to eventually use. So they would have, even in the early stages, meetings with the collaborators from ESA and internationally to make sure that everyone was on the same page and the telescope would be successful.
Thank you.
Sure.
Yes, I was just going to, we were talking before about some of the results of all this technology. We looked forward to the magazine when I was working for them back in the 80s, and it was called Spinoff. And they were very proud of how much, and rightfully, their miniaturization and how they adapted, how some of their technology was adapted in the industry. So there was a lot of, why are we doing all this? Why are we spending the money? Well, the spinoff was supposed to help address those issues as far as what does the general public get out of the space program.
Yeah, absolutely. So that's kind of what I was speaking about. They still do that. They have people who their only job is to look at the applications for space and see how we can actually use that here on Earth, which is really exciting. They do a lot of research on the International Space Station too, about how there's been developments in medicine that have been made through some of those experimentation and research efforts on the ISS that are really interesting to learn about, and just know that each technology that we develop for spacecraft and our space exploration, we try to apply here on Earth too.
So the mirrors, what happens if they get hit with a meteorite or damaged somehow?
Yeah, that's a great question. So there have been, we're at L2. Now, if people are familiar with like LEO or lower Earth orbit, that's where you have a lot of the satellites that are Earth observing satellites. There's some debris that's present there. At L2, there's definitely not as much that has been launched and operated at L2, but it is still something that has been considered. So they've, performed analyses, and they're always tracking kind of the environment around the telescope. So they've definitely planned and done analyses to see what would happen if there are micrometeorite impacts, but it isn't too much of a concern for us.
Okay, someone put something in the chat here. Let's see here. What exactly is the L2, and is there an L1 or L3?
Yes, there are multiple Lagrange points. I'd have to confirm exactly, maybe Jennifer knows. I have to confirm exactly the number of them. Are there 5 Lagrange points, Jennifer?
Yeah.
If you're okay, yeah.
Yes.
So you can see here that it's, Webb almost has its own little mini mini orbit that it's in at this L2 point. If you ever heard of kind of like a three body problem, but it is, still in this orientation with respect to the Earth, Moon, and Sun, as it goes through this L2 orbit.
Oh, a question about the NASA employees who worked on Webb all this time.
Mhm.
Are there a lot now who might be getting laid off, or do you have other projects, and are they staying on with NASA or your
Well,
future?
yeah, absolutely. So what is really beneficial for the upcoming programs, like we talked about the Roman Space Telescope, we talked about LUVOIR, is that we have the expertise. Some people have worked on Webb since it was just a concept when they were designing it. And those people are now working on ensuring that we've documented all of our lessons learned as they, have been throughout the mission. It's really important to NASA that as we make new discoveries, as we learn lessons, that we document them and ensure that following projects can benefit from those lessons that we've learned. So those people are working on, first of all, documenting all the work that we did on Webb, any lessons learned, if there are future recommendations for the next projects. There are some people who will continue to support Webb at that Space Telescope Institute. So I know a group of my coworkers that once we launched, my role on Webb kind of transitioned and I'm now working on Roman, but people went directly to the Space Telescope Institute and they plan to stay there as long as Webb is operational, which could be 5, 10 plus years. And others are now on new projects. So we have lots of missions that are occurring here at Goddard. We have some really exciting work. So I can say that people are using that expertise that we learned on Webb and applying them for our next future missions. And there are also some others that work on the, proposals for new projects that haven't even been accepted yet. So there's really a wide variety of what has come next for a lot of people that supported Webb for so many years.
Okay, and then someone said that because it's an international telescope, that scientists will all around the world will be applying to, use the telescope.
Mm-hmm.
What is the first project that they'll be undertaking?
That's a great question. I'm actually not sure what their first project is. Like I mentioned, the early release science program, they did make selections for that, and I'm not privy to that information, but every observation that they do make with Webb will become public knowledge. And so they will in the future have, further proposals that come through for observation time on Webb. But it'll be really interesting. I mean, you can have, again, people from around the world apply for time and make a case as to why we should use Webb to look at this specific target.
And then, so you're going to be working on the Roman. Can you tell us how that telescope is different from the James Webb?
Yeah, absolutely. So I mentioned before that it is similar to the size of Hubble's primary mirror, but they actually have, it's a wide field view. So I think they're going to be able to see actually like 100 times more than the field of view that Hubble had. It's been really interesting because I'm now supporting this mission and it's in the earlier phases of development. Whereas with Webb, when I joined, it was already in the integration and testing phases. So I'm getting to learn a lot about all of the different components that are making up the Roman Space Telescope, and just it's exciting to see the mission in a different phase of the project.
Okay.
I also just wanted to mention.
Oh, go ahead.
Go ahead. That's okay. I was just going to mention that, since my background is in contamination control engineering, you'll see a lot of photographs with people in, they're called clean room suits or bunny suits. So here you can see the only part of this person that is exposed is right around their face. And this is especially necessary because our largest contributor of contamination is actually the personnel that are working on the hardware. So as you can imagine, we don't want any skin cells, we don't want any of that contamination being generated by a human to end up on the telescope. So you have these clean room suits that everyone had to don, and throughout every stage of the project, whether it was just like bench level work, working on an instrument, all the way up to an entire observatory, we've been mitigating the contamination for the telescope, and they seem to be getting great results while in orbit. So it's always a challenge working in the clean room, but every person that's been near this hardware has had to don those bunny suits and the clean room garments in order to protect the telescope.
Someone has in the chat, do you see that they will have to repair it? Will they have to send people up to repair it or do any work on it?
So right now, I mean, Hubble is actually a lot closer. So with our current technology, we were able to go and service Hubble. With Webb, we are much further away. We actually, at this point in time, do not plan to go and service it, but the space field is always constantly developing, and who knows, maybe one day we might decide that we are going to go and send, even if it's robotic servicers or possibly astronauts someday, to go to L2, but not at this point in time. We need to make a bit more progress in that field. And there are missions like the Artemis mission at NASA where we're talking about how we can get to Mars and get humans to Mars. So we're definitely on the path to increase our presence in space and putting in the effort to make that possible.
Okay, does anybody else have any other questions they'd like to ask at this time?
I don't have a question, but I just want to say how terrific this has been. Great program, and thank you.
Yes, of course. Thank you so much for having me. Again, it's great that everything about this is public. So if you're interested in learning more about Webb, I can share some of the resources with Elizabeth, and the NASA homepage has a blog where they post almost daily about what they're doing with the telescope at the time. So it's really interesting to see and follow along each step of the way.
Thank you. But about the budgeting, does it look hopeful going forth? Say if administrations change, are you folks going to still get enough money to work?
So I definitely have no involvement in the budgeting, but I will say that from one administration to the next, I think it shouldn't be a problem at all. I've found that there is lots of work going on here and lots of exciting future work to come. So no, I'm not concerned about that.
Okay, that's good.
Anyone else? Well, Elaine and Jennifer, thank you so much for your time. We know you're very busy people, and we appreciate all this great information. And thanks everyone for joining us today, and we will see you next time. Thank you.
Thank you all so much for your time. Thank you, Elaine, for a wonderful
Yes, thank you.
presentation.